Hi guys, welcome again to my Atari YouTube channel for the 8-bit personal computer. My name is Steve, I'll be the instructor here again. And what I'm going to go in to teach you today is something I've kind of capped on in my display list video. Is actually something called display list interrupts. I want to kind of show you from basic how to set those up, and I have it set up here in the background, and how the machine code looks from the data statements. We'll extract that bit by bit, and I'll show you exactly how the bytes look and how they translate into machine code. So this is going to be for an advanced level. So if you're not an advanced person, you'll probably get lost on this one, and I apologize, but I tend to go more of a focus toward the intermediate to the advanced person based on my experience and where I've come from. I could still teach beginner courses if people request them, but I haven't got any requests. But I do want to thank you guys, because I was pretty amazed today when I actually finally got back and checked my YouTube account after a couple days. I actually had suddenly 11 new subscribers. That's amazing. So if you guys are definitely interested, pass it around to people. We'll keep this moving, this ball rolling and everything, and just see how it goes, because I think the Atari has a chance still. You know, even though the PC and the Mac and everything is kind of taking over everything, the Atari is still an essential machine, because there's still people that actually like to use it just for fun, maybe games or stuff like that. It can be, you can actually buy them on eBay pretty cheap. I do recommend, if you go on eBay, make sure you check out the person that's selling them. I bought a few on eBay that never actually worked, so be very careful there. So anyways, let's get looking at this one. It's going to kind of pivot the screen again here. And bear with me on my camera. For those of you who are new, my camera, it's one of these Samsungs, I don't know, and sometimes it comes in focus, sometimes it loses focus. Looks like this time it's going to get a pretty darn good picture. So I'll explain this step by step. And okay, so what we're looking at here at the very top here, this is actually how you initialize what's called a display list in your computer. If you need more information, you can actually check that out in my display, it's a tricky word to say, display list video, which I have posted here on my channel. So what this actually does is it sets up the initialization of the low and the high byte of this display list interrupt. And you can set this variable to anything you want to call it. I just called it start here because it's, well, I guess it's a starting place. And then you multiply it by 256. That's how you get the high byte calculated in here. And what it's going to do is it's going to take two numbers. Like, for example, if you look down on this line, we'll jump back up here in a minute. 0, this would be the low byte. Oh, this might not be the appropriate byte for this, but this is an example. This is the low byte of location 512, and this 6 is the high byte of location 513. And if you take those two together, you take 0 plus 6 times 256. If you pay attention here and look at this, these three numbers here, 1, 2, and 3, the 0 is actually representing the, what did I just lose it here? Yeah, I just erased it on my screen. Let me pull it back up there. It's line 10, I think it was. Oops. Like typing blind over here. Okay, so the 0 actually represents, as an example, if this were actually set to peak 512 and plus peak 513 times 256. So think of this 560 having a number, but in this case, this is actually going to represent this first number, which is the low byte. So the low byte is calculated first, and to get the full address of the number, which when you see, you know, this calculation didn't come up. Let me redo that calculation here. I wanted to show you that now. Moving on ahead. So right there, 1536. So if you look at the second number, it's going to be 6, because that's the high byte of the number. So it's taking the first number plus the high byte, and you multiply 256. This is how it actually calculates a full address in I guess you could say the assembly language or whatever, the Atari computer. And this 1536 is actually calculated to make up this address. So in this case, we'll use the example of this one, which I think I still have it in memory, so let me see if I can pull it out of here. You know what, I think it didn't initialize it. Let's do this. Let's just set this as a stop. We'll run this and get it in memory. Okay, so it's got the DL in memory here. We'll go back to that line. Oh, you know what? I'm using DL, excuse me. A lot of my videos I initialize them with DL, and this one it starts. Excuse me, I did not see that. So start. If I can spell it. So start. This is the full location of the start that's making up this full address, and here's how it breaks down. I'll show you step by step. So to take it, remember you take the low byte of the number, which is 560. We'll get a number for that one. That's 32. And then you take the high byte, which is obviously the next address in line for 561. And you can almost guess what you have to do here. Anybody know what to do at this point? If you look at this number I showed you earlier, 0 plus 6 times 256 is exactly what we're going to do with these two numbers. So 32 plus 156 times 256 equals none other than 39,968, which is actually the screen address, excuse me, the start of the display list in memory. So, knowing that, let's move on to the program. Remove my extra line here. Move to the next step here. Okay, so I won't go into a lot of explanation on this next line because if you need to know more about display lists, I recommend seeing that video. But this is basically setting up the display list in memory, starting at scan line 5 all the way down to 20, and it's just poking that in memory, and it's set in 130, which is, I think, setting it at graphics 2 or 1 or something like that. Probably 1. I use 1 a lot. And then this is just a variable I called for the address that we're going to initialize next, which I'm going to manipulate page 1536. So we're going to point the display list in memory to 1536, or 0 plus 6 times 256. Remember the high and the low byte. So we're going to set up, I just set up a variable called PGM, and we equal it to the value of 1536. So this page is actually for PGM equals 1536 to 1536 plus 15. It's just an easier way to put the number in there and calculate it. And then you're going to read a byte, and basically all it's going to do is go down here and start reading in our display list interrupt, which is actually stored in machine code. When you see the numbers like this, that's machine code. Or machine language, I'm calling it machine code. Okay, so the next thing we would do is we're reading, to kind of explain this kind of for the novice or the people who are kind of new to the Atari and maybe the basic programming in general. When you first read a byte and you're going through the loop, it's going to read the first digit or the first byte number on that list. In this case, byte, once you read it the first time, it's going to have a 72. It's going to go all the way through the loop and look for the next. When it hits the next, it's going to return back to the 4, follow through the whole thing. Remember, it's going sequentially, and it's going to read the next byte in the list, which will be 165, and it'll keep doing that as it's going down to each individual byte until it gets them all in memory. And that's basically what it's doing, is it's poking what's called page 6 of the Atari computer in memory. And I'm just having this set up this way so to show you what it's doing is you can use any location that's acceptable in memory for basically that can store machine language programs and doesn't run into stuff like your basic interpreter, which holds your compiler for your basic, or any other things like your screen registers, your player muscle graphics, your redefined character sets, and anything to do with your I/O calls and stuff like that. So as long as it's not interrupting anything, then you should be good to go. And to kind of clarify that, I've showed this a few different times, but I'll keep reiterating it for clarity. The Map in the Atari book is your most important resource, which you can also get a PDF on the internet for this. I've actually got a few links on my channel to show where you can get this book at, because it has an amazing layout here of all the display lists, the addresses stored in your computer, where you can actually use and direct them and activate them through the pokes and stuff like that. So what I was trying to tell you earlier is in page 6 here, let me find pages. Pages are stored in 256 increments. So page 1536, I'm saying page 1536, I mean address 1536, excuse me. They're not labeled at the top by the direct addresses, and then some pages it has a couple different addresses, so it's not always easy to find what you're looking for. Let's see, 1792. The 1792, that stores the DOS interpreter and stuff like that. So it's right here, actually. I always think it's good to clarify by holding the book up. So it's right there. It's page 6. Bytes protected from operating system use. Page 6 is not used by the operating system and may be safely used for machine language subroutines, special I/O handlers, alter character sets, or whatever the user can fit into the space. Kind of just what I was going over. So in general, as long as you look for that in this book and find addresses like that, there's also 32767, which is an undersafe place to store them. and you can store them also in the DOS area of 1792. I forget what it goes up to. Actually, it's right here, 1792 to 5377. It'll overwrite portions of your DOS, but you can use them and write them into there too as well. It really doesn't matter, because anytime you type in DOS, it's going to store it in memory, and it doesn't stay in memory because when you hit the reset key, you can easily override it. So what I mean by that is you can't type DOS directly in BASIC and instantly go to DOS. As an example, if I just type DOS, DOS here, it's going to run. I'm not going to do it because it's going to actually try to find my DOS disk. It's going to run and look for that disk in memory, but it has no way to look inside of your addresses right now to see DOS until it actually loads it into a diskette. And for those who may want to know, who are maybe newbies and just picked up a computer and used to the PC generation, this is the diskettes that they use in those days. It's a 5 1/4 inch. This is just a DOS Atari disk, and this is how you access the stuff. But we're kind of getting a little bit off of and going on a tangent here, so let me kind of loop back around. If I just thought a little bit extra information might be a little beneficial for people who want to know. Okay, so what we're doing here, we're storing it at page 6, and then this right here activates the display list interrupt. 54286, and I wanted to pull it up in the book, and you know what, I had my finger on it and I lost it. It's right here. So 15, here we go, trying to zero this in here. It's called I don't know what the non-maskable interrupt enable. Poke with 192 to enable the display list interrupts. There's different stuff you can do it, like bit 7 will set up a display list interrupt instruction, any display list instruction, blah 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 blah. There's different stuff you can use it for BBIs and stuff like that. So basically, that's how you activate the display list interrupts. And this is actually what I really wanted to get into this video to explain about. This is the machine code that's being read in earlier by our location 1536. And I'll kind of prove that to you right now and show you that these numbers are actually being stored in memory. We ran the program once earlier. Let me make sure to run it once. You're going to get a glimpse of what the program does. It's basically what it's doing. Hopefully it doesn't make you blind, but it creates a luminance of lines on your screen. So we take the location of 1536 as they indicated here, and we'll copy in this line right here, by the way, plus 15. And if you peek into these values, you can read what's stored in there. So I'm going to read in 1536, 1537, 1538. It's going to print this out on the screen. I'm going to concatenate it and put a comma in it so it shows up on the screen. It doesn't just scroll straight down on the screen here. It's going to show you all these numbers. Look here, these are the identical numbers here. So it's basically storing these in page 6 so that we can access them with our machine code, which is the next step I want to take you to. Machine code. Okay, so down here on the next line, you see this first data statement that actually says 72. This is actually known as, what do you call it, mnemonic or something? Instruction. It's an assembly instruction that's being stored in assembly language. And I want to show you this other book I have. It's actually, it's an antique magazine I have from the January 1986 issue or something. Or 85, I don't know if it's even going to come in. There it is, 1985, so January 1985. And this magazine's pretty cool. Actually, in the back of this, they have a list of all of the machine language instructions, and they show you actually the byte codes for each of these. So basically, we can find out what those numbers represent. And remember, I was showing you earlier on the screen here that we have the first one at 72. So if we look up 72 in the list here, I think it's on the first row. Let me go up, 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 up. I think it curved over here. I'm gonna kind of, page is getting old. I've used this so much, it's just kind of getting used. So anyways, you can probably see if they look real close, it says 72, 48, HPHA. So basically what the first line is doing is pushing to the accumulator. So I'm not going to go over all these in general. I mean, I could. Maybe I'll go over a few more of them. But what this is doing is how you set up and push a value onto the stack whenever using the display list interrupt. You want to always push the value, or this is just pushing the accumulator in general because we're going to be manipulating the accumulator. Accumulator keeps track of all the processing that's going on in like the X registers, Y registers, Z, and all that stuff. So the next instruction here is actually a two-part instruction. If you look at the lines here, this says 165, 203. This is LDA. This is the 165, and this 203 is this page 2. Well, excuse me, it's address 203, which is unused by the basic interpreter. So you can safely use this one as well as 204. Okay, so what I'm going to do is I'm going to look up the 165 and kind of demonstrate. Let me look at it here first. I don't have to kind of move it around a little bit. I found it's right here at the bottom. So, see right there where it says 165A5 has a little character after it. It says LDA AA. Basically what that's doing is it's loading the address for the, well, I think it's called, excuse me, I think it's the low byte or something. But what it's basically doing is it's allowing you to access anything into the lower course in memory, which I believe is just in page 6 or something. The 0 addressing, that's it. It's load accumulator is 0 addressing. You know, we're going to remember this eventually. So we're going to load the value that's being stored in 203. Right now, since we haven't stored anything in 203 and it's being unused, there's not going to be anything in it. But very soon we're going to put something in it, which is actually what the next lines are going to do. So remember, those are those first 165, 203. The next one here shows 230. And again, to make this easier for reference, you've got to bear with me. I'm going to show you again in here. Because if you guys don't know in the book, it probably won't be fair to you to kind of see how this is really going on and how the computer's looking at it. It's right, oh, is it over here? I'm sorry. 230, there it is. See it over here? It's actually, let's just see how fast I can find it here. I work blind here. It's right, that's right here. There it is, 230. So 230 says, or did I just have it there? It says increment AA. You see that increment AA? So increment the low addressing in memory. At this point, we're going to increment, since we're using 203, we're going to be increment the value in 203. So if we increment a value in 203 and it has a 0 in it first, and we haven't stored anything in it, it's going to be a 1. And increments again, it's going to be a 2, a 3. It's going to keep incrementing in memory. So basically what that's doing right now is it's using 203 as a clock, basically, so to speak. The next two lines are actually the next two locations here. So remember, what we just did is we went, well, first we had these two, and then we went to 203, so 230 is the increment, the 203 is the address 0 page for the 203. The next one is something called I think it's called no operand. It's actually the location 234, 230, well, it's 234, so we got it here twice. So I won't show you this, since that's basically all it shows on here is the no operand. What it basically is, it's a way to skip, how would you say that? Not like a cycle, I think it's called a cycle. The way to skip a cycle in memory, basically. So to skip, it's like to skip a space or something, skip a timing, so that you can move on in kind of like a little wait period. So something's going to happen. I'll demonstrate this with and without it, just to kind of show you how that works. But we'll get back to that. Okay, so the next thing here is we're going to be using, remember, right after the 234 here, we just go to the next instruction. This is actually a 3-part instruction. So you look here, it says 141, 24, 208. So what that's doing is it's saying the 141, we'll go back to the book here, and again, we'll get so, kind of bear with me on this. This is just for newbies and people who want to follow it. So right there, you see it says 141, 8D, store AAAA. So this is basically going to store, it's going to allow an address of a high and a low byte to be stored into an address. That's why it's a 3-part instruction. The first part is going to have the store instruction, or the instruction you're using, and then it's going to have the low and the high byte here. So basically what that's doing is it's translating the 24208 into this number. And if you remember earlier what I showed you, you just type the number 24 plus 208 times 256, and that's how you calculate the number. So basically what this is doing is it's taking the accumulator with 203, incrementing a value, and it's storing it in here. And the 53272, I'm pretty sure that's a color code or something. Let me look that up real quick, just for clarity. 5372. I just lost my page. I just had it right here. I showed this one in another video, but I'll show it again. So it's 53272. So it's the color and luminance of playfield 2, which is 710. So what that's basically doing is it's controlling this background. Because if I type in poke 710, let me first of all save the location here, so I'll lose it. If I type in poke 710, we'll say 0, for example, that's just changed the background color. So what this is basically doing is it's allowing you to access the displayless interrupt, what's it called again, the masking or whatever. the playfield, excuse me, the playfield. So it's allowing you to access the playfield so that you can manipulate the colors that are being stored in the screen. Now if you try to use 710 in here, it doesn't work. It takes control of the entire screen. It would just flash the screen. So let me restore that here. Whoops. Oh, you know what? I should have well, let's just reset this. Easiest way to get it back. Okay, so the next thing we're doing, we're getting pretty close to being done here, is we're going to skip down to the next page. I'm sorry, the next line, which would be a two-part instruction. And the two-part is 201, 255, which translates into compare number 255. So if you look again here in the book, the compare instruction is just it's a simple compare. So basically what it says is what you're looking at here. I won't show it, but it's very similar. It just says compare the number, and then it just shows a little number sign, and it shows NN, represent a number. So compare number 255. So it's trying to see if you've already gone through 255 scan lines at this point, and if you haven't, then it's going to use the next instruction, which I'm going to go over here in a minute. Okay, so moving on to that one, we got the keep track of myself here. We got the 201, 255. So now we're moving on to the next two-part instruction, which is 208, 245, and that corresponds to obviously BNE RP. So this basically means branch is not equal. When a branch is not equal to something, it means it's not finding this value of 255. It means the branch could end up, the number, it's basically looking for a number, and this number, if it's 200, if the branch is not equal. If it's 1, it's not equal. If it's 255, it's basically going to go past this point, because the branch is actually going to do a loop. It's going to keep going back and forward into the program. So once it's equal to it, it'll drop out of the loop basically. You know what? I just cut out the program. Let me just reload this again. Oh, you know, I erased the line on here. Let me add that back in. Probably almost done. So we're got down to 64 is the RTI. Okay. Well, there we go. Okay, so the next line here, well, before I go to that one, let me explain this very carefully. I want to show people how to calculate this, because you can learn to calculate machine language within actually BASIC once you really learn how it works, and you can actually learn how to use the branches to go back and forward and stuff like that. I learned to write them this way, so I don't have to sit there and put in my assembler cartridge or my Mac 65 cartridge and write the program and then get the numbers and then or save it to disk or whatever and go back and just hope it's working. It's better to actually learn it this way if you just want to work within BASIC and manipulate machine language. So what we're doing here is we're going to branch to RP, and I just called this anything just so I can kind of branch back to the actual location. But here's what it's doing. Notice it says 208, 245. Again, the 208 is the branch not equal. If you don't believe me, look in the book. I'm going to show you this one just so that we can kind of stay consistent here. So it's right down, oh boy, right there, 208. So branch is not equal, and it says AA right there. So basically, again, the branch is not equal to the zero-page addressing. It's going to take and start counting this backward. So right now, it's showing 245. That's the location we want to get to. Now keep in mind, anytime you're using a branch, or if you're using a branch equal, you're using a branch carry set, a branch carry clear, it's going to have to go to some kind of direct memory addressing. So what this is, the way you calculate this is think of this right here as 255. It's kind of where a branch cannot go beyond 255. So basically that means you'd be trying to jump out down into the program somewhere where it shouldn't be going. So what you do is you start counting backward. So 255. And we're looking for 245, by the way, so we're going to count until we get to 245 backward. 255, 254, 253, 252, 251, 250, 249, 248, 247, 246, 245. So here's where it's going back to. And remember, the 230, 203 is actually this line right here. Load accumulator 203. I'm sorry, increment 203. I had it in there earlier and I erased it, so let me just stick it back in there. It would look like this in assembly. This could just stand for repeat or whatever you want it to be called. Oops. and then you would just name this down here repeat. So it's basically going back this line. And you can also look at it this way if you can't understand this. Just count again. 255, 254, 253, 252, 251, 250, 249, 248, 247, 246. And I probably miscalculated something here. It should be at 245. Let me see. Oh, that's right, because this is a 0 2-part addressing. Let's try that one more. Remember, the 0 2-part addressing is the 3-part addressing is 141, 24, 28. So that's where I made my mistake. Let's try that one more time. It's 255, 254, 253, 252, 251, 250, 249, 248, 247, 246, 245. So then we've gotten basically back to that line. So you can also change this if you wanted this, for example, just to go to this line. You would calculate it forward this time. So remember, this is 245, and we're at the 230-204. So we would go forward and just count from the number that we were trying to get to, which was 245, 246, 247, 248, 249. So let's see what happens if I change this to 249. Hopefully this does not crash. I'm going to save it just to make sure. Oops. Always a good idea to save in case something goes wrong. Machine code is so easy to trap your computer and lock it up. Oh, so what was it again? I know I was going to forget it. So it's 240, 45, 46, 47, 48, 249. We'll change it to 249 here. We'll rerun it and see. Whoops. So you notice how it changed earlier. The lines were kind of bigger. This time they're kind of going down a little bit faster. So basically what it's doing right now, it's not incrementing back to that 203, so it's not able to see what the next line is. So it's kind of just going through the loop as it was without a branch. So it's going a little bit faster. But notice it still worked when we did that. So let's just kind of play it around with it a little bit more so you can kind of get the hang of this. So we had 45, 46. Let's go to 247 this time and see what it does, out of curiosity. And that's kind of the similar. You couldn't really tell much of a difference. But I just noticed my screen is kind of... Okay. So let's try the next line. You can kind of bear with me on the patience on it. This is a tutorial, remember. This is so that you can really learn how to count in machine language and really learn how to calculate things and basically how to write your own code in BASIC and access it through the interpreter that way without having to go straight to December. So the next thing we're going to try to do, I was going to take out these two operands and see if we can get something else weird to go on. So we're going to basically be losing some things in memory. So it's going to be a little tricky now. So what we're going to be doing is we're going to be taking out these two instructions, 234, 234. Now when we do that, we also want to indicate up here in the loop that we've now got 2 bytes less. So where are we reading? Right here, 15. So now this is going to become a 13, which is 15 minus 13, or excuse me, 15 minus 2 would be 13. And down here, here's what it's going to look like now. Basically, we just lost these 2 lines. So let's kind of work off these 2 lines and we can recalculate where our branch needs to go. So remember, 255, 254, 253, 252, 251, 250, 249, 248, 247. So it's going to be the same number. So we can actually leave it the way it is here. So nothing's been interrupted that way. Because remember earlier we changed, it was 245, but then we took out the 2 no operands and that just left it with the 247. So let's see what this one does. See how it's kind of changing each time? And this time it's not using no operand anymore. So if you saw when I first ran it, it actually, and I could probably put that back in here, it shows the scan lines going straight down the screen and you can actually see the colors. This one you can't because there's nothing slowing it down. Oops. Let's put them back in there real quick. I'm going to show you exactly how it looked earlier. Where was we at here? Right after 203. Should do it. There we go. Now you can actually see the scan lines again. So that's kind of an introduction to this one on Display Less Interrupts. I'm going to go ahead a step further here and show you some other stuff I can with the display interrupts. I was going to kind of take this a step up. Wanted to see if, now let's just do that. I wanted to save this first. Actually, you know what? I wanted to show you one more thing here. This is kind of cool too. What we're going to also do this time, I wanted to see how long this video is, 30 minutes. We're going to change the borders here. And we're going to use our machine code instruction. We're going to manipulate our remark statements here so we can see how the machine code works. And that's another thing you'll want to get in the habit of doing too, is just set them up in remarks here after you're calculating them or putting them in here in the list. Then you can see exactly what's going on. It's a lot easier than just trying to read these numbers and going through this book basically and trying to say, okay, what does that instruction do? So first of all, we're going to calculate and find out what the border location is. Before we do that, we want to look up in the book here and see what the next playfield would be. Remember 53272, that's the playfield for 710. So for 712, it's just two more. It's 53274. So we're going to use that next instruction underneath here. I'll just call it 155, like that. So remember, once we manipulate something here, we need to change it up here, and our branch is now changed again. I'm just going to put the branch label back in here. So we know 20, oh, no, 24, 141. I already know this one by heart, but it's going to be 26. And I'll just show you how I calculate. Whoops, what did I do wrong? Oh, I haven't done that in a while. I just shut off the TV again here. Give me a second. It's going to take a reset. Man, that button is like in a bad spot. I go to like try to turn this TV and I hit the power button and it turns off. It should turn on in a second. Okay, I just pressed it. Sorry about that, guys. Okay, I'm going to check my screen here, make sure it still looks good. I think we're okay here. Okay, so basically we got an error message there, and it was just because I was trying to enter inside the line and it wasn't able to read the full data statement. So it's fine that way. I'm going to show you how to recalculate the branch for this. Remember, it's 245, and you can probably almost do it yourself by this time already, I imagine. So we're going to be counting backward again, starting at 255. And this time we want to get back to the same place, but since we added 3 new bytes, we just need to basically count this backwards. So basically you can just calculate the number backwards by 3, and that'll be 242, but we'll count it down here just for beginners that are still trying to keep up with this. So 255, 254, 253, 252, 251, 250, 249, 248, 247, 246. No wonder I got 246, and I said this would be 45. I guess I had 3 in there, 48 or something. Oh, I'm going to double check that real quick here. Remember, you can also check it up here. You don't just have to do it down there. So 255, 246. You can go 55. I just like to count this way. It's a little bit faster. 55, 54, 53, 52, 51, 50, 49, 48, 47, 46. So that is correct. It's 246. And we'll rerun this one, and it works correctly. It should be changing the border at the same time as changing the screen. So it's going to basically turn out this black and turn these into colors as well. And something just went wrong. Hopefully we didn't lose our program. Let's see here. This is why you have to be very careful with machine language. If you're not, sometimes you can lock up the computer. Obviously I made a mistake there. Let's see if we can correct it here. That's why I didn't think that calculation looked correctly. I think, let me count my numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 18. Oh, I only have 13 up here. I forgot to change this. Remember, we just added 3 new bytes up here. This has to change. Okay, and that was it. There we go. So now it's actually going all the way across the screen, and it's changing the border as well. Earlier it was actually leaving the black around here, but now it's changing the entire screen. Want to save that. night. Okay, so I think I have one on this disk, DLI2. Let's see what this one does. Oh, that one wiped out, whatever it was. Let's see. It wiped this out, whatever happened. Let's see. There it goes. Okay, so this is another display that's interrupt. It's basically changing the colors down the screen here. Notice it's got a little bar down in here, and you see a little cursor down here. Back this up a little bit. Try to see the whole screen. So let's see what this one's doing. Oh, look at that! Did you see that? It actually went in and it changed some of my code here because I probably didn't set the addresses correctly, and it this is what I was trying to tell you earlier. It's overwriting my basic program in memory. So this code is being stored in memory line by line, and the computer must have ran to an address that was actually overwriting the actual code that I had as a listing. So just basically load that back up and see what happened here. We'll do some investigating. Whoops. Ah! I think we got a lockup. I'm trying to run load. This is a good example though. Now probably in this video here, it actually just it locked up my disk drive now. It's actually erased some portions of my access from my disk drive to be able to load programs, so it's no longer accepting that. So I'm gonna basically have to reboot here for a second. But you might have learned something there, I hope. We'll go back and we'll check that program out if we have a little time here. Now we're going to load up the other program again. This time we're going to load it, we're not going to run it. For beginners, oops, I just lost my screen here. Oh, come on camera. The camera has decided to go kaput again at me. Oh my gosh. I can't wait till I figure this camera out. It's like, it picks up, there it goes. It seems to pick up funny movement and it throws things off. Move this back a little bit. Okay, so what I was just explaining earlier here is, if you have a program in memory and you don't want to run it, you would just load it instead of running it. Earlier you saw me run it, and you've probably seen the main load a lot of programs into memory. But you can also put a run command here and it'll run the program. But earlier when we ran that, something was wrong with it, so it crashed the basic compiler basically. I'm just curious to see what happened here. Let's see. Because the first line looks fine. This is start memory. This looks fine. It goes 130. It's probably the machine code that crashed it. 32. Fuck BGM. BGM. There's something to do with the machine code. Make sure we got the full number of bytes for the machine code. We got poking in 32, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 6, 7, 8, 9, 10, 1, 2, 33. This says 32. I can tell by looking at this right now that something doesn't look correct here. It's 50, 100. And as I was reading these as scan lines or something, I don't know what this program was doing. They were supposed to take a set of characters on the screen and change the colors of them. Let's investigate that. To investigate it, we're going to take this apart in machine language. This will be your lesson on this one. I have a lot of it memorized already, so I'm just kind of going to go through it. I think that. A little bit faster, I think. I remember 138 is how it was transfer X accumulator. I can almost see what's going on right now looking at it. I think it probably didn't pull a value off the stack and it crashed. Let's see, where am I at? 1, 2, 3. So we're increment 2, 3. Increment 203. I think that one's load. Go to the X register. 3. 189. And that one's store. That's now load X. Okay. 2. That's calculate 6. 64. Hopefully this one doesn't bore you too much, but this is really going to teach and take you a step up with your assembly code. So bear with me as I start translating this back into machine language. Where was I at? 1564. Okay. Increment X register. I'm up this location. X register. There's a X register 4. Now we're going to branch back to 4. I'm just going to put a 4 in there, or a number for now, a label. Figure out what that is in a minute. 0. Let's see, 170. We're almost done here. We're right here. That should be it. So let's go back and look at the code here, and then we'll look at the machine code that I just put in here and kind of make sure that it looks correct up here. And I think our branch might be looking kind of funny. I notice it says, this is branch 4, so to calculate 4 you have to go forward, so it'd be 0, 1, 2, 3, 4. So basically it's going down here. Maybe it is correct. Okay. Okay, that all came on the screen, just what I wanted. Perfect. Okay, so once again, we're going back and we're translating the machine code. I won't use this magazine since we already went over this earlier, unless we come across something really important. So the 72 is pushing the accumulator. The 138 is transferring X to the accumulator because we're going to be using it down here. And then you just push back to the accumulator when you're doing a return from the interrupt. Then we're going to increment 203, which is 230, 203, the two-part instruction. And then the next one here is going to load a high byte. So remember, it's going to be 3-part instruction. So 166, where was I at here? Oh, yeah, I skipped this one, didn't I? I skipped this, excuse me. Load the X register 203 is 166, 203. And then we're going to use a 3-part instruction over here, which is 189, 28, 6. And you might have saw me calculate that earlier. And I hate to do it here. I'm probably going to lose some of the code down here, but we'll do it. Anything over here. So it's 1564, so this is the next number here. I just wanted to show you that, even though I have it down here. So earlier I took 28, which is the 2-part from the store instruction, or from the store instruction here, and we just calculated 28 plus 6 times 256 to get that high byte of that number. The next one is a 3-part instruction, which is store 10 to 12, and again we're going to take 10 to 12 times 256. So the next one is 54,282. That's a 3-part instruction. The next one is another 3-part instruction. This one is 141, 26, 208. calculate that one. Oops. So that one is 53,274. So we just did that one, 141,226,208. The next one is called compare the X register. So this basically means compare the immediate number value that you put after it. In this case, you know, I put 4 on here. Did I do that right? Let's double check that. 220. Oh no, I'm sorry. I skipped a step here. We're going to increment the X register, which is 232. So that's by itself. The next one is a two-part instruction, which is 224.4. So it's compare the X register with number 4. So basically, we're checking for 4 scan lines. And keep in mind what this is doing for the beginners is it's loading the value of 203 here, storing a value in here, and increment that value, and checking to see when it equals 4. So if it starts at 0, we're going to wait until it counts at 0, 1, 2, 3, 4. Once it reaches 4 here, it's going to jump out of this loop and it's going to do the next instruction. But because right now the branch is not equal to the 4 yet, we're going to loop back to the, actually we're going to loop forward in this case. Usually we loop back, but this one I notice it's looping forward. That might be the mistake we need to correct. I notice it's looping forward here, so it's going 0, 1, 2, 3, 4. It's going down here out of the loop or something. Now let's see here. So we're over here, 28204. We'll come back to this one in a minute. The next one is going to load the accumulator with the immediate value of 0, and this one is right here. So 169 is LDA 00. The next one is a 3-part instruction, which is, I'm sorry, 2-part instruction because it's accessing the 0-page addressing again. So it's 133.203, and that stands for, translates into store 133 into 203. Remember, the 203 is unused location by basic. And then the next instruction here goes down to 104. This is actually pull. And let me put this back on the screen so you can see that. Still up here on the screen. So right here, where it says 104, this is the pull. The next one is 170, that's transfer X. Let me look at the book here, because I always say that's transfer X to the accumulator, and I don't want to sound like I'm misquoting that. It doesn't even tell me here, it just says TAX. Okay, so I'm just going to say it's, well, basically it's restoring the X register. Earlier you transferred onto the stack, and you're basically pulling X register back off the stack. So this is pushing the accumulator, which you have to do it twice. I'm sorry, I'm up here, I meant to be down here. So pulling the accumulator pushes what you do first, and then you pull. See, when you push the value accumulator here, and you use it in here later, if you go down here, it's going to pull that value back off the stack that you can use. And sometimes when you pull values, you can use them inside of parameters and stuff like that. But in this case, because the computer's already using it, you would actually just pull the value back up. Okay, so after that, we're going to 2 pulls. We're going to return from the interrupt, which is a 64 here. So basically, it's going to return from the interrupt. So let's we know this one crashed earlier, and it put in some funny code. Let's go back and look at it here and see if we can kind of figure out what happened. Because when you're playing a game with interrupts like this, you can counter stuff like this. I think we didn't have enough bytes up here or something. It was. See, apply 12.0, page address in. This all looks correct. Start. Is that one correct? 560 plus B plus 61, that's 256. That part looks good. 303. 220, that looks fine. That has something to do with this probably. Read byte code PGM. Oh. What is this one doing? Code PGM. Oh, that's it's incrementing through the pages. So 1536, that should be correct. Next PGM. I think it has something to do with the values here, and it's not pulling off the right values or something. Let's see. So I'm going to count them again. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 9, 30, 31, 32. And this is a 33. We have a 32 up there. Aha. Most importantly, I think what has happened here is it's going. Let me relist this to show you. what I did here is I've gone back and I've added in an extra byte here, which I noticed was missing from here. And what it's actually doing without the extra byte here, it would have gone through our display list interrupt, but when it got down here, it would not see this line. If it can't return from an interrupt, it's going to crash because it's now able to pull that values back to the accumulator. So I think that might have solved it. I'm going to save it just to be safe. If not, it was a pretty good lesson, I hope. Was it 2? It's 2. Okay, it's done. I go back to double check the machine code again here. A pull or push pull TAX DXA, that looks fine, that looks fine. Up here's the X register, this loads 203. Let's check this location to make sure that's not anything funny. 54282, what is that? Here's what that location does. What I'm doing is I'm going through and I'm checking these locations here that are being interpreted from the assembly code here. So it's 54282, and the book down here says this about it. It's called Wait for Horizontal Synchronization. Allows the operating system to synchronize the vertical of the TV display by causing the 6502 to halt and restart 7 machine cycles before the beginning of the... Where'd this go? No, it's on the next page. I flipped it over. So to calculate from the beginning of the next TV line, it is used to synchronize the vertical blank interrupts or displayless interrupts with the screen display. So I think it was probably just something else to do with that, but basically it's how allowing the displayless interrupt to work. I'm pretty sure we used this in the earlier example, and this is just going to be the location. I think this is for the border. So let's double check this one more time. I mean, it looks good here. I'm going to run it. I hope for the best. Well, that time it didn't change our lines, so something went correct. I think it's reading too many lines now, though. Let's go back to that error message here. I want to show you that too about error messages. I've got my book. Where'd it go? If you want to look up an error message here, if anybody has this book or a similar owner's manual, you can look up the error messages in the back of this one. I don't know what this one's doing, but I wanted to show you guys. Let's see, what page is that on again? I think it's right before this. It's been a while since I've used this book. It's right here. So the error message for 6, right here, says out of data. The read statement requires more data items than the data statement supplied. So when I put that 32 or 33 in error, it was reading too many lines. So let's go back and correct that. So basically that wasn't the error. It wasn't because it was reading the RTI. It might be something else. It might still crash, but let's hope for the best here. Anyways, even if it does crash, you still learn, save it here, how to translate another program into machine code. I hate this lopsided monitor. Here we go. Ah, we got it to work. So something's going correct. So basically what it's doing is it's controlling, this one I wanted to show you. It's controlled the scan lines here in the border, and it's manipulated them in different colors as it's going down. And it's not controlling this, although it's still controlling this in a way in the screen, because we didn't set a location to actually change the screen. So basically it's going through here, but because there's no display line set up here in like the 54, this is one, the 53274 and not 53272, which is the screen background, it's not able to change this. But if we add that in, we can easily make the lines go across. Let's do that to kind of wrap up this video. Hopefully it doesn't crash on me. It just did. Wow. I gotta restart again. Doesn't look like I'm pretty incompetent, but I'm teaching you how to translate code into machine language at least. Something's going wrong with that one. I'm gonna look and play with that one later. It's just because whenever you're manipulating display list interrupts, if something is wrong in the way the code is going, it's going to crash your basic program. You've seen how usually that one crashed. It might have also been because I pressed the keyboard, which you never want to do while it's running. So we're going to add in our new line. Finish up the session. 23272, and we're going to put in our new machine code for that. And where was I at here? Let's go back. So 232, it's going to be right before that one. Here's the compare. Here's the first one. Let's stick it right there. So 24, 208 is the translation of this number. So 24 plus 208 times 256 equals 53,272. Now we also, because we added new data in to our read statement, remember what happens if we try to run it right now? It'll give an error message. Actually it didn't. But it actually did what I wanted to. It took them all the way across. That's what I wanted to generally is show you. It'll take the lines all the way across now, because now it's actually controlling the border and it's also controlling the screen. I don't know, these weird letters came down here. It looks like the ready statement got split up. That's kind of interesting. See, when you're playing with display interrupts like that, you can make kind of weird things like that happen. Usually it'll just say ready down here because the program has ended, but for some reason it's moved this line over. It's kind of really strange, isn't it? Notice you can still see the Atari screen up here. The blue screen is still remaining because we haven't changed the graphics mode, but it's manipulating those lines or the display lines in your computer, those raster ones. It's probably going to be dead again. Let's see. Actually, that time it didn't die. Isn't that nice? Let's save it. Whoops. Ah, it did. It actually killed the disk drive again. So I'm just going to go ahead and wrap that one up. I think you've got a pretty good idea of what's going on here. And hopefully this hasn't been a complete waste of time. This has actually showed you something in general. I just wanted you to kind of learn how display list interrupts work and also how to translate basic data statements into machine code so that you can actually see what's going on step by step. So kind of use that one as something, a guide to fall back on, even though it's been crashing a lot on us. You can still kind of play with it and see if you can get it to work actually. See if you can kind of beat me to the finish line for this one. So if you're interested, go ahead and subscribe. I promise I'll get some better videos up than this one. This one was just kind of a test to kind of see where we could go with this one, kind of playing with stuff. That's one thing that's really important too. If you want to really become like a good Atari programmer or just a programmer in general, learn how to test stuff, learn how to take risks with your computer and stuff like that. Just don't do any hacking or anything like that if you're doing anything over the internet. Just kind of play with things. You can't really hurt your computer. There's no way to really burn out any chips in the computer or anything like that. So kind of, take it to the limit. As I say, the sky is the limit. So anyways, until next time, thank you for watching.